All right, so the record is on. What we'll be talking about today is going to be a new module. So the new module is the von Neumann architecture and memory. Um, the the first two modules, would be these two, D flip-flop and other basic memory devices, and also, tracking change propagation. So if you had a chance to read ahead of class, that would be great. If not, that's okay because this is what I will be going over today so that you can get the horrendous lab done tonight. So you have been warned, which means you might want to pay attention and potentially take notes. All right. So with all that said, we'll get started. So the first thing is to take a look at the circuit that you'll be looking at tonight, in the lab. So we'll be focusing on just what you need to know to get the lab done. So the device that you'll be working with tonight in the evening is going to be called an SR latch. Okay, and there are multiple versions of an SR latch. This one is NAND gate based. So instead of giving you a diagram, okay, the notes, excuse me, gave you a text description. Okay, so this is a semi pseudo object oriented programming kind of approach. Okay, so you can see that NAND input pin. Let me magnify the uh, text first because people in the back may have some trouble reading it. There we go. So NAND to input pin, output pin, you can see they all start with the uppercase. So in C++ programming, anything that starts with the uppercase is typically a class name, okay, which is what you use in order to create objects. So that means your N1 and N2 are NAND 2 gates. S and R are input pins, Q and NQ are output pins. So that's basically how we create all the parts. And I will construct the corresponding logisim circuit so that you can actually see how everything correlates. The next four statements, okay, which is circuit dot add node blah blah blah. So circuit is really just an object, which is the actual circuit that we are creating. Add node is a method of circuit. So that means we are invoking a particular method of the object circuit. And what we are doing is we are creating a new node. So I'll talk about what a node is. A node is essentially a electrical connection, a single electrical connection that connects multiple what we call ports together. Okay, so those are the terms that we have used in Logisim, from before. So because S and R are just input pins, so there's only one port, and that port is just called a pin. N1 and N2, on the other hand, are NAND 2 gates. So that means they have two input pins. So between those two input pins, I'm just going to call the first one, I look at it as an array of two input pins. So the first one would be in bracket 0, referring to the first input port. And then the second one is going to be having an index of 1. So I'm borrowing the concept of array indexing in order to address one of two, potential input ports of an NAND2 device. And then we also have outputs because N1 and N2 are NAND 2 gates, so they also have a single output. So this is the output of N1, this is the output of N2. So this is how we specify how things are connected, okay, in a very symbolic way. If you are going to become a computer engineer, this is basically a really simple language, to help you understand how do we describe the connectivity between components of a circuit, but without using a diagram. Okay, there are many other languages. Okay, VHDL is one, Verilog is the other one, and both of those are called HDL language. HDL stands for Hardware Description Language. All right. So what we'll do next is we'll actually draw the circuit, and then we'll start to analyze what happens when you change the input to that circuit. Okay, so there's a particular standard that we're going to use in tonight's instruction, and your lab is going to have to follow exactly the same convention. So before we go any further, I also want to point out if you want to read or if you want to have the AI to read for you, how that standard is used. It is also in this module, okay? Tracking change propagation. There we go. So it is its own module. This is a really, really short module. Okay, I'm not going to read the module because I'm going to demonstrate to you how this is done. Okay, but just in case you want to have Gemini to help you understand the material while you're doing the lab, you can certainly do that because this instruction is consistent with the instructions of the lab, which is also going to be something that you will need to do for the second exam. Okay, so this is not in the first exam, but it is definitely going to be in the second exam. So there we go. So we have all the resources. And now I'm going to go back to Logisim to create that circuit. So I hope you guys remember, okay, I'll I'll actually, I'll let you guys take a look at the text description while I'm constructing the actual circuit. Okay, so I'm going to do this little trick here that turns out to be quite useful in my classes because this way I can select only a portion of a window and always display that when I'm working with a different window. So there we go. All right. So we can see that we have input pins, we got output pins, we got NAND 2 gates. So let's go ahead and create all of those things first. So what I have already done is I'm selecting an input pin. So I'm going to put an input pin here, call this one, S, and then we'll do a duplicate and move it maybe down here and call it R. Okay. So what I'm doing is I'm really just instantiating the objects. Does everybody understand what I mean when I say a class in object-oriented programming and also what an object is in object-oriented programming? Okay, very good. So now we got some output pins. Okay, we only got two of those. So I'm gonna stash this one over here, call this Q, and then I'll make a duplicate of that and then change that one to NQ. There we go. And this one is gonna be NQ. Excuse me. And we also need two NAND 2 gates. So the gates are all located here, and the NAND gate is this one. So it looks huge, okay? Because we don't need it to be that huge. We only need two input pins instead of five. So this is how we create, two NAND 2 gates, and I'm gonna space them out, a little bit more, and move the pins a little bit here. Get this one over here, get this one over here, and then the output pins can kind of match the position of the outputs. Okay, there we go. All right. So now we have the six objects created. Okay, the first three lines of code create these six objects. So now we are going to create the nodes. So we'll focus on the first line of creating or adding a node. So that's connecting S dot pin, which is the only port available with an input pin, to n1 dot in bracket 0, which refers to n1's first input port. Okay, so I'm also going to name the NAND 2 gates just so that it's easier to carry on the discussion. So we'll call this one N1 and we'll call this one N2. There we go. So now everything has a name. It's easier to kind of identify. Oh, okay, that's not what I intended to do. All right, so what we'll do is we are now making a single wire from here to here. That is a node, okay? In other words, a node is essentially the copper on a motherboard that is making electrical connection between the ports of your components, okay? But there is a difference between a wire and a node, okay? Because you can have multiple wires still be considered as one single node because everything are connected electrically, okay? So as long as it is one single electrical connection, it is considered one single node. So I'm going to handle the two easy ones first, and then we'll work with the ones that are a little bit more hairy. Okay, so there are these two, which corresponds to the first two lines of circuit dot at node. So the next two lines is a little bit more interesting because they connect three ports together. So if you look at the second to the last one, it connects the output of N1 to the first input of N2, also to Q dot, the only port of Q, which is an output pin. So the way we draw that is there's no way I can draw that in one single stroke because I can only draw one wire at a time. So I will need to kind of tap the wire to here and then hook it up kind of like that, put it here. There we go. So this is corresponding, okay, and let me use the poking tool to highlight what I mean. This, okay, what is highlighted right now is corresponding to the second to the last line. This is one single node, even though it is made out of two wires, okay, it is considered a single node because it is one single conductor that is interconnecting three ports in this case. So are we doing okay so far? Understanding the differences between what a node is versus a wire. So we all good? Okay, all right. So now I'm going to work with the last node. So to work with the last node, I have to go back to use the selection tool because that's the only way I can draw a wire. So it is very symmetric to the first one, and except I kind of have to offset this a little bit. And there we go. So now we have a little device called the SR latch. Okay. So later on, we'll talk about what S really represents and what R is representing. But the first thing we want to do, or the first thing that I want to do, is to show you guys how to understand how the circuit is going to work. Because this is a little strange, right? Compared to the other circuits that we have talked about. This one is a little strange because looks like we got a strange loop going on here, right? Because the output of N2 becomes one of the inputs of N1, and in return, the output of N1 becomes one of the input of N2, which makes the analysis of this circuit a little bit interesting. Okay, so what we'll do next is I'm going to turn off simulation. Okay, so I'm going to say disable simulation and then reset, so that everything is just blue. And the reason why I want to do this is because I want to analyze this circuit step by step, not using Logic Sim. Okay, so we're going to do this using a spreadsheet. Do we have any questions about the circuit itself and also how the circuit is corresponding to quote unquote the text description? No questions? All right. So the other reason why I want to at least introduce the concept of using text to represent a circuit is because let's just say that you want to become the next billionaire working for NVIDIA as a computer engineer. Okay, so how many gates are in a single NVIDIA GPU that is intended for use with a like AI data center? Hmm? Like a core, yeah. Well, it's huge, right? The number is huge. We can actually try to look it up. Okay, so I'm going to go back to the browser. This one. Okay, there we go. I don't think I need this anymore, so I'm going to take it away. So we'll just go ahead and ask how many gates are in the latest NVIDIA GPU for AI data center use? Okay, there we go. So we are looking at 208 billion. Okay, hundreds of billions of transistors. Now, those are not gates. They do not release the specific number of individual logic gates, but you can do a quick estimate. So it doesn't really quite say that, unfortunately. Mm. But it is okay. We can do a rough estimate. Okay. Um, each NAND 2 gate is only using two transistors. So with the device that we were talking about, that will only take, no, I take it back. Each NAND 2 gate has four transistors. So eight transistor will make a single SR latch. So if you divide this by eight, it is roughly, let's call that 25 billion. Okay. So there it has 25 billion gates. So do you want to have a gigantic Logisim screen in order to specify how the billions of components are interconnected? My guess is no. Okay, that would not be doable. It would not be feasible at all. Okay, so that's why when we design complicated devices like this, or even just these processor in your cell phone, okay, which is an ARM chip, which is by comparison a lot simpler. Okay, we still don't want to do it graphically. Okay, we want to use a text representation. It is basically the same reason why you're not programming in flowcharts. Instead, you have C++ programming, right? It's the same reason. Okay, so that's the motivation. Okay, that is the reason why I introduced the text representation in this class. But our focus is not so much the text representation. Our focus is more about Hmm, I wonder, okay, how do we figure out what this circuit is going to do depending on how we change the input, okay? So that's going to be the focus. Um, all right, so let's go ahead and do that. And I'm going to do kind of the same thing, okay? I'm taking a little screenshot over here and make it always visible. And then we will switch to a really cool mechanism for tracking the behavior of this device. And you guess right, it is a spreadsheet. Okay. In this class, you will basically see how tech can abuse the concept of a spreadsheet to do a lot of stuff that people do not really intend to use spreadsheets for. Okay. So let's go ahead and take a look at the spreadsheet, and then we ask, what are we looking at? Okay. It looks colorful, okay, a lot of pastel colors, um, and it's not Easter yet, right? I mean, Easter egg usually has all these colors, and I'm not even religious, so that is totally irrelevant. Okay, so but we do notice a few things, okay? What do we notice? Oh, I think we remember this type input pin, okay, and one of the input pin is called S. There's another input pin called R. There's a NAND 2 gate called N1. And how come N1 is taking up three columns instead of just one? Because each port is one column. Okay, so in 0 is one port, in 1 is one port, out is one port. So columns D, E, F, they all belong to a single NAND 2 gate. Okay, two for the inputs, one for the output. Are we doing okay so far? Okay. What about N2? Kind of the same thing. We are using columns G, H, and I to represent in 0 of N2, in 1 of N2, and also out of N2. We have two output ports. Q is an output port, NQ is also an output port. So are you guys convinced that all the ports are now represented as columns? What about the interconnections? That's where the color code is coming in handy. Okay, so there are two things you can use, for understanding the connectivity. One is the color. Okay, so when you look at the yellow color, it is corresponding to the node that is connecting to the S input pin to the first input of N1. Okay, if I were to use a mouse pointer, The yellow columns is corresponding to this node right here. What about the output of N1? Okay, it is connected to two other things. So the output of N1 is right here. So you can see the green color is corresponding to the node that connects from N1's output to the output pin Q, but also connecting to the first input of N2. Those are all corresponding to the green columns and etc. Okay. So if and I put numbers too, okay? So for people who are colorblind, who cannot differentiate the colors easily, I also have a node ID, which serves exactly the same purpose, because we can see the yellow columns are labeled 0. The green columns, there are three of those. They're labeled 3. The purple ones are labeled 2, and then what is the remaining? The blue ones are labeled 1. Okay, so this way, people who are colorblind can look at the node ID. People who like to look at colors can just look at the colors. Are we doing okay so far? How the spreadsheet is set up to represent exactly the same thing as the circuit itself. Okay, all right. So what we'll do is we'll start with the initial stage of both input pins being 0 and 0. Okay, so NC is the abbreviation of node connectivity. Okay, in other words, on each row of an NC, we are basically saying, okay, who else is connected to node 0? Okay, so I'm going to say, okay, node 0 is right here. So if this node 0 has a 0 because it is an input pin and the end user decides to change it to a 0, then this one is going to be a 0 as well. And if a blue one, which is this one here, is a 0, the other blue one would also be a 0. So this is how we work with an NC row that has two bold-faced states here is simply to propagate that using the node connectivity. In other words, we are basically saying, okay, since everything of in node 0 are electrically connected, so when one is changing, then all of the other ones would also change to exactly the same state at the same time. Are we understanding that concept? Is electricity. This is just purely because of electrical connection. Okay, we are propagating the value because of electrical signal and also because of the copper on the motherboard. Are we good? All right. So the next question then is, what about PD? What is it representing? PD stands for propagational delay. Okay, so propagational delay has to do with the logic gates are not instantaneous. Okay, the logic gates are not instantaneous because it has got transistors, and it has the transistors require some time in order to change the output. So I'm looking for a dry board marker, and I'm gonna borrow this from our dear PCS division. So what does a NAND 2 gate look like? Okay, I hope you guys still remember this. Okay, we have uh, two P-type transistors over here. Okay, two P-type transistors. Oh, okay. So two P-type transistors, like so. And then, the exact diagram is not too important. Okay, I'm just, showing you the rough, you know, display of the circuit. Okay, and obviously, this is not working out very well. I'm gonna put it back into the box over here. Okay, but the idea is a transistor. Okay, so I can go back to Logisim and kind of use that too. So this time I'm gonna pull a transistor because I just need to talk about the device a little bit. Okay, so we go to wiring and then we pull just a single transistor out, and then we just kind of zoom in to the transistor. So a transistor like this is called a MOSFET, which stands for metal oxide semiconductor. Um, FET is field effect transistor. Okay, so okay, it's not really super important, but there's a capacitor here. Okay, because these two are actually not physically or electrically connected, so it has a capacitor effect. So when you have a capacitor, then to change the state of one side of the capacitor in order to change the other side, it takes time. Okay, it's like, kind of like a balloon. Okay, so if you want to say, okay, I want this balloon to be blown up or I want this one to be deflated, it takes time. Okay, the electricity to charge the capacitor also has to go through quote unquote resistance as well as inductance. This is not a device physics class, so I'm not going to go deep into, electricity and why, there are delays. But the whole point is, in order to turn on, in this case, a P-type transistor, when the input or when the gate changes state, okay, when the electrically something in the input pin has changed state, it takes time to turn on the transistor. There's a certain delta of time in order for the transistor to be quote unquote turned on from the time that the input pin has changed its state. That's all I'm saying. Okay. In other words, the best way to see this is look at a transistor like a faucet. Okay. And when I say, okay, turn on that faucet, I need to water my garden. Okay, there's going to be a delay, right? Because it takes you time to turn that knob, and then after you turn that knob, it takes time for the water to go through the pipe, and then it takes time for the whole thing just has a delay. It is the same thing with a device like this. It has a certain delay. So that means when you change the input pin, or when you change the input port of, in this case, N1, the output doesn't change right away. Okay, there's a certain delay to the whole thing. Are we doing okay so far with that concept? Okay, all right. So PD is that delay. Okay, so when I go back to the spreadsheet, which one is it? Nope. All right, so I'm gonna have to minimize this. Okay, there we go. All right, so on the PD row, we have to document how the output of a device is changed because of a change of the previous NC row. Let me say that one more time. And when I say something one more time, usually it means it's kind of important, and I want to make sure that you guys are catching it. Okay, I'm only going to say that much. So once again, a PD row is indicating the change of an output of the output of a device because of a change of an input of the same device from the NC row that is right above it. All right, so that's what I said. Okay, so now we have to say, okay, look at row number 5. Okay, look at row number 5. What is changed? Well, obviously, input pin S is changed, but input pin S is not a device itself. So there's nothing that can be affected. Okay, same thing with input pin R. Okay, it's just an input pin. It is not a logic gate. It does not have transistors. So there's no delayed effect whatsoever associated with the input pins. Excuse me. And then we look at column D. Column D is one of the input pins of N1. Aha. But N1 is a NAND gate. Okay. So that means it has got transistors in the inside. So when you change the input of a NAND 2 gate, the output is got may be changed. Okay. Potentially it may be changed after a certain propagational delay. Are we doing okay so far with that concept? You change the input pin or you change the state of the input of a NAND 2 gate. After a short delay, the output may be changed because of the change of the input. Is that concept okay? All right. So now the question is, okay, we are looking at N1's first input, which is in zero, being changed in the previous N0. So now the question is the output going to change from unknown, okay? Because when you see something that is blank, it is unknown. It actually has a question mark here to indicate it is unknown. But is it known now? So this is a tricky question, okay? Well, okay, I'm gonna say this is not a tricky question, okay, because it looks tricky because we only know one of the two inputs of a NAND 2 gate, and I'm asking you what is the output in this case. So the way to answer this question is something that we practiced on Tuesday. Do you guys remember the first question that we answered on Tuesday? And what tool is super duper useful to answer that question? Starts with a T. Yes, a truth table. Okay? So in this case, we can also use a truth table, except we have to use a truth table of the NAND gate or the NAND operator as opposed to just and or not. Okay? So now the question is, do you remember the truth table of NAND? Now, if you say, yep, absolutely, I actually totally remember the truth table of NAND, great. Okay? On the other hand, you go like, no, I don't remember the exact truth table, but I know what a NAND is. I can work that out myself. Okay? Then it is still great. Okay? For people who are thinking, I have not heard of the concept of a NAND gate, I would start to worry just about now. Okay? Because that's actually a really important concept. So, do you guys want me to work out the truth table of NAND, or do you think you can work it out yourself? So you can work it out? You cannot. Okay. So I'm going to do one thing to convince you that you can. And this is not a political campaign. I hate politicians when they turn something as simple as I can into a slogan. Okay, you guys are too young to remember that. Anyway, what is NAND? Okay, so X NAND Y is what? How do I expand X NAND Y? What, say again? Okay. Okay, but how is it expanded? Why do we call it NAND? That sounds like a pretty funky name. It's a negated AND, right? So, okay, give me the C syntax to re-express X NAND Y. I don't have the notes in front of me. I don't have it projected on my shirt here. So looking at me is not going to help. Okay, so do you have it in your notes? If the answer is no, then I'm going to ask why. Okay, because these are important definitions. Okay, so does anyone want to look it up for me? It is the negated and. Okay, so think about negated and. Okay, negation only takes one input. It negates one thing, right? So that means it's unlikely that I'm negating just x or I'm just negating y. I'm negating the result of an and. Negated and. Okay, so what goes onto the two sides of ampersand ampersand? What are the only two things I haven't worked with? There you go. So knowing that this is NAND, can you work out the truth table? Just say yes. Okay, very good. Okay, now that we have gone over this your problem, we'll continue with our simulation. For those of you who are still kind of thinking about the truth table, work it out in your own time, okay? Because it is something that we have talked about already. I believe that was day one of this semester. And the great thing is, I record all my lectures. I can actually prove that I talked about this on day one of this semester. I do know also, how annoying what I just sounded, but that's the truth. Okay, the truth sometimes is annoying. So when you have to fill in that evaluation form thing, just say that it's not tech who is annoying. It is the truth that is annoying. Okay, truth table back here. Can we determine the output of NAND gate N1 only knowing that one of its inputs is a zero? Okay, so what is the output? Yep, exactly. Very good. Okay, the output is a 1. And to explain that, okay, you can just kind of go look at the definition. Okay, so we know that x is a false. Okay, if x is false, the AND is guaranteed to be false. Not false is true. So that's how we know. Okay, but having the truth table available is going to be a lot more visual because you can just look up and go like, oh, what happens when if I know at least one input is a 0, the output is going to be a 1. Okay, so having that truth table is going to come in handy. All right, so that means I can kind of make the same conclusion about N2. The reason why I can come to the same conclusion with N2 is because the previous N0 says one of the two inputs of N2 is also changed to a 0, and that's because the input pin R is changed to a 0. So that means the output of N2 is also guaranteed to be a 1 at this point of time. Okay, so after a certain propagational delay, N2 is also going to be a 1. And that's it. This is all we do with a PD row. Okay, so in other words, a PD row only indicates changes of the output of logic gates as a result of a change of input pin of those logic gates from a previous NC row. So now the next row is going to be another NC row. Okay, the reason why the next one is going to be NC row is because, oh, if we are changing the output of N1, then whatever that thing connects to using a node is also going to be changed to a 1. Are we doing okay so far? Okay. So typically, I cannot say always, but typically only one port connected to a single node is the output of something. Okay, all of the other ones should be inputs. So at this point on the next NC row, I can now say, okay, who else is connected to this one over here? So for people who are not colorblind, we can just follow the green columns. For people who are colorblind, we can follow the node ID. So we're looking for everything that is connected to node 3. Column G is also on node 3, so we put a 1 over here. Column J is also connected to node 3, we put a 1 over here. Okay, does everybody understand why those ones are on the next row? Because the the two ones, okay, meaning cell G7 and cell J7, those are on row 7 because those are the changes because of node connectivity. It's not because of the logic gates. Okay, so if we change all the green ones, shouldn't we change all the purple ones too? The answer is yes. Okay, because if this is a change, okay, then all of the purple ones should also change in the NC row, which is here as well as here. So are we doing okay so far? Okay. So now that we are on an NC, now that we're done with an NC row, the next one is PD again, which means we only want to look at row 7, and then we ask the question of, is it changing the input of any logic gates? We are not too concerned about column J and column K because those are output pins and they are not logic gates. Okay, so we are not too concerned about those two columns. So we can focus on the other columns. So now we look at column E, okay, and we go like, okay, you got changed. Are you an input to a logic gate? We look it up, go like, oh, yep, this is an input of N1. So now we have to say, okay, with N1, which is an AND gate, should we change its output? In other words, we are now trying to decide, should we put something here? Because that cell, which is F8, is corresponding to if the logic gate N1 is going to change its output, this is where we need to indicate the change. So what do you think? Nope, no change, right? We're all good. Okay, so that means I just took care of analyzing N1. So this is a steady state. There's no change. But there's another logic gate that has at least one of the input ports getting changed, and that's N2. Because N2 used to be unknown, it is now a 1 because of the previous NC row. So now we have to look at N2, and then we ask, what about the output of N2? Is that going to change? Which is here. Okay. Nope. I take it back. One more step. There we go. So you can look up the truth table again. Okay. Or you can just plug it into that equation. If at least one input of an N2 gate is a 0, the output is guaranteed to be a 1. It is already a 1. It is not a change. So we don't put anything in the cell, which is I8 in this case. Okay. So that means, oh, we have an entire row of PD that is empty. There's nothing in it. Okay. So that means we have a steady state. This is called a steady state. So let me go back and refer to row 8 as a whole. If there are no changes to the output pin of any device after a PD, after a propagational delay, you have reached a steady state, which basically means all the changes that can happen has already happened. It is now at a point where without any input changes, the circuit is not going to change any state at this point. Are we okay so far? All right. So now we're going to make some changes to the input pin because otherwise the circuit is not going to be very exciting. Okay, this is static. So we are going to change this one and this one both to 1 and 1. And both of these are boldface. Okay, so when you see boldface, it means it's a change because of the user. Okay, this is not a change because of the circuit itself. This is this is a change to the input pin, which the end user is going to have to trigger. Okay, but I'm changing both of them to ones at the same time. So now you go like, this is going to be boring because it's going to be looking like the previous several rows, except everything is going from 0 to 1, and we're done. Well, not quite. Okay, this one is going to be a little bit interesting. First thing first, on an NC row that has input changes, the first thing you have to do is to propagate those changes of the input pin to everything else connected to the nodes, corresponding to those input pin. So this is yellow, this is yellow. Put a 1 over here. This is blue, this is blue. We put a 1 over here. Are we good so far? Okay, so this is still node. It's those changes. Those changes are because of node connectivity. So now we move on to PD. So PD is asking, according to the previous row, which is row 9, did we change the input, at least one input of a logic gate? There are only two logic gates here. We look at each one and then we analyze. So we first look at N1 and then we ask, did we just change one of the input pins of N1? Yep, we did, right? Because we just changed input 0 or in 0 of N1. So now we have to look at the output of N1 and then we ask, is that going to change as a result? Okay, so we put a cursor over here and then we ask, because of D9 getting changed, does it trigger a change after a propagational delay at the cell, which is F10? We go yes, right? Because if both inputs of an NAND gate are ones, the output is a zero. Very good. So yes, we caused the change. So we put a zero here, and then we analyze N2 the same way because according to row 9, um, in one of N2 just got changed. So that means I have to reanalyze the output of N2. If there's no change, we just leave the cell empty. But this time it's changed to zero as well. Because in zero was a one already, in one just got changed to a one. So we have one one as the two inputs of N2. So the output of N2 is going to change to a zero. Okay. So now we have to go like, okay, we have to go for another NC. The green ones just got changed, so all the green one of the NC row will basically copy the same value. The pink one is just changed, so we're gonna update all the pink ones on the following row, like so. Okay. Then you go like, okay, we're getting back to PD. So if the circuit is symmetric, that means we're done. This should be a steady state. But don't make the assumption. Okay, so we're going to analyze, are we really at a steady state? Okay, so we look up row 11. There's a change over here. It is a change of one of the inputs of N1. So we're going to have to figure out, is the output of N1 changed as a result of that? So that means I have to put a cursor over here and ask, is that going to change as a result of row 11? What do you think? It does change. It's changed to what? To 1. That is correct. Okay, it is changed to a 1. What about the other NAND gate? Okay, the other NAND gate also saw a change in the previous NC row from a 1 to a 0. So we have to reevaluate its output, okay, which is here. So what do you think is the output of N2? N2 currently has in 0 being a 0 and N in 1 being a 1. 0 and 1 is a 0, not 0 is a 1, but it was a 0 before, so it is now changed to a 1. Okay. So now we have to go for another NC row, right? So the next NC row is going to say, okay, because this is a 1, all the green ones are going to be updated to a 1. Because this is a 1, all the pink ones also update to a 1 over here. Okay. So now we have to evaluate it again. Okay, so we have to scroll down to the next row. Okay, I know it's getting a little bit harder to read. Let me do a full screen first, just so that it's easier to read. Okay, there we go. So now we're looking at row 14, and in row 14, we're looking at row 14 to basically ask the question, um, after a certain propagational delay, is the output of N1 or N2 changing because of the changes that we observe on row 13? So you look at row 13, okay? Remember, these two columns, J and K, are not really important, okay? Because they are output pins. They don't have logic gates inside. They don't have transistors inside. But when you look at this guy here, it's like, oh, okay, that's a update of in one of N1. Okay, let me scroll back up so we can see the title. There we go. So that means when we look at the output of N1, it is supposed to be a 0 at this point. That's over here. There we go. This should become a 0 because that's a 0 because in 0 of N1 is still a 1. That 1 is going to stay the whole time because that 1 is because of the input pin. Okay, the circuit itself cannot change its own input pin. But in one of N1 just got changed to a 1. 1 NAND 1 is a 0. When you look at N2, kind of the same thing happens because we just changed in 0 of N2 from a 0 to a 1. But when you look at in 1 of N2, that's tied into one of the input pins. That one is not going to change. But nonetheless, now we have both inputs of N2 being 1s, which means the output becomes a 0. It was a 1 before, so now we have an update to a 0. So we put a 0 right here. Okay. So now we have to go for another N0. Okay. But you can probably recognize at this point that row 10 and row 14 are exactly the same, which means now we have an infinite loop because we are now back to the very same condition that we had on row 10. So that means the next row will look exactly the same as row 11. The next row is going to look exactly the same as row 12. The next row is going to look exactly the same as row 13. And then we go back to row 14, and then the whole cycle begins again. Which means, in this case, the circuit is never going to settle on a steady state. This circuit is now oscillating. It is not going to settle on the steady, in the steady state. Is that okay? Now, if you guys are not convinced, we can go for maybe a few more rows. Okay, just kind of go through the usual reasoning. So this is changed. Okay, so the next green one was going to change. The green one's going to change. This one got changed, so the pink ones will change too, like so and like so. This is changed from a 1 to a 0, and as a result, this is going to change to a 0 back to a 1. This got changed from from a 1 to a 0 as well. So now this one is going to change to a 1 as well. So now we can see how row 12 and row 16 look exactly the same. So yep. Say again. If you put it into, I think what you meant is an oscilloscope. There is such a thing called a spectrum analyzer, but in this case, it's not going to be the spectrum analyzer. So if you put it into an oscilloscope, you will see a square wave because it's a 1 and a 0, 1 and 0. When you look at the output pins, yep. And the period of the wave is exactly indicated here because when you look at how the output is changing from a 0 to a 1 and then back to a 0, this is the period. So the period of the square wave is determined by the propagational delay. It's basically twice of the propagational delay. So if it takes 5 nanoseconds for the input change to affect the output for the NAND 2 gate, then the period is going to be 10 nanoseconds, which translates to what, 100 megahertz as a frequency, because it's 1 second divided by the period. So are we good so far? Okay. Does everybody understand how to use a table like this in order to track down how the circuit is going to change? So we are good with this? All right. So this is basically what you need in order to do the lab. Yes, it won't it won't settle. There's no steady state. But it has to be coming from 0, 0 into 1, 1. Yep. It has to go from 0, 0 to 1, 1. Can you ask that question again? Can you ask that question again, please? If you only change one of them from a 0 to a 1, but leave the other one alone, it will still be going to a steady state. Yep, that is correct. If you start with 1, 1, then the output would still be unknown because it just preserves whatever it is. Yep, that is correct. All right. So since I have talked about everything that you need for the lab, now we will take a step back and take a look at why are we even doing this? Okay, so we are basically going all the way back to the name of the module itself. Okay, the name is called the von Neumann Architecture and Memory. Okay, so the question is, who the heck is von Neumann? So we'll go ahead and do a little Wikipedia search. Okay, I know Elon Musk is making his. What is the name of Elon Musk's encyclopedia? His little AI thing to replace Wikipedia. You cannot. Okay. No, Grok is the AI chatbot. What is the name of Elon Musk's uh, replacement of Wikipedia? There we go. Alternative. There we go. It is called Grokipedia. So you're partially correct. It starts with Grok. It's powered by AI. Interesting. Hmm? But I'm not going to Grokipedia. I'm going to Wikipedia. There we go. And we are going to look up Von Neumann. Von Neumann. Von- Okay, so we have to be more specific because he's an interesting guy. Um, and then we'll look up his name. We'll look up the person first, and then from there we'll look up the other stuff. So this dude is John Von Neumann. A little bit interesting, from the perspective of a scientist, an engineer, and whatnot. Okay, he does overlap with Albert Einstein as a professor at Princeton University. So they did overlap a little bit in terms of time. Albert Einstein is Jewish, and this guy is Hungarian. Okay, and this guy likes polka music of all things. He likes to listen to polka music when he's working on his problems. Albert Einstein, on the other hand, likes quietness. And since they share the same hallway, you can kind of imagine the kind of things that they get into. Because one guy is just playing loud Hungarian polka music. And if you want to know what is Hungarian polka music, go to YouTube and look up Hungarian dance sorting. There's a whole bunch of sorting algorithm illustrated by dancers, doing Hungarian dance with Hungarian polka music. So yes, I can relate computer science to just about anything. Anyway, this guy is interesting because when you think about Albert Einstein, okay, what is he good at? You go like relativity, okay, physics, maybe just maybe quantum mechanics, okay. He hates quantum mechanics, but he actually gave birth to quantum mechanics. So you can kind of think of quantum mechanics as the bastard child of Albert Einstein because he gave birth to quantum mechanics or quantum physics, and then he says, "No, this cannot be my child." And then the other guy called Bohr, okay, the other scientist, the actual person who discovered quantum physics through Albert Einstein's mathematics. He basically says, "Nope, the DNA matches. Here's yours." Okay, so if you're intrigued about, Albert Einstein's contribution to physics and how he objects quantum mechanics, like, really loudly, and then eventually we prove that, yep, you're so brilliant that you have just invented a whole new branch of physics that you do not even believe yourself, but your own math proves it. So that's a pretty interesting kind of side branch, for those of you who want to get into quantum mechanics or quantum physics. So anyway, take a look at what he is good at. Okay, he is good at mathematics, physics, economics, computing, and statistics. Then you go like, well, maybe he's just like tech. So what do people say about tech? Tech of all trade, master of none. Okay. Unfortunately, he's not one of those people. He's actually a master of everything. So he's good at every single field that is mentioned here. If you ask any person of any field that is mentioned here and ask, so what do you think of your John Vonnegut? They will all go like, he's a genius. He's the best in my field. So he's the best in every freaking field that is mentioned here. So kind of interesting history. Unfortunately, he passed pretty early. Okay, so when you look at his lifespan, he died when he was 53. For reference, I'm over 55 now. Okay, so I can say I'm older than John Vonnegut when he died, and I got more hair too. so, so now the question is, what was his contribution to computer science? How many people have heard about the von Neumann architecture before this class? Okay, I'm glad a few people have, one at least. Okay, so the von Neumann architecture is interesting because we just take it for granted. So now we have to take a look at computer architecture before John von Neumann. So I think ENIAC is one of the computer that is not a von Neumann architecture. So I think, yep, there we go. Um, okay, very good. I think this is a great picture of the ENIAC computer. So when you read the subtitle, okay, let me go back to read the subtitle first. So it says right here, okay, the subtitle or the description, says Glenn A. Beck in the background. I guess it would be this guy over here, and Betty Snyder, who's going to be the woman over here in the foreground. They are programming ENIAC in BRL, which is some kind of programming language, in 1955, okay, ish, okay. Then you go like, doesn't seem to be typing anything. There's no console, there's no keyboard, there's no typewriter of any kind. So how can he be possibly programming a computer? Hmm? Say again? Nope. Nope. Punch cards are like light years ahead of this. Okay. Exactly. Okay. So the behavior of this computer is dictated strictly by the physical wiring, which means in order to change the program, quote unquote program, to do anything else, you're going to have to unplug a bunch of wires and then reroute those wires to where they're supposed to go. That is before von Neumann architecture. Okay, so before von Neumann architecture, the behavior of quote unquote computer is strictly based on wiring, like physical wiring. Okay, so if you think about it in today's term, okay, it means over the air update is not possible. Okay, it also means every time your operating system has an update, you probably have to spend like a year or so rewiring all the connections because of the complexity of the program that we have. The equivalent number of changes to the wiring is going to take you at least a year if you can get a tiny little tweezer to get to those tiny little wires on your in your computer. Okay, So we can probably appreciate the contribution of von Neumann because without John von Neumann, we can reduce the size of transistors all we want, and it won't help anything because in order to specify or to change a program, you have to change the wiring, the actual physical wiring of that thing. So you can get the smallest transistor, the same size that we have, which is in single digit of nanometers. Okay, great. But the wiring to do all the interconnection between the transistors will be so heavy, we won't have drones. All of the technologies that we are talking about, I don't think we'll even have self-driving cars because the wiring alone to specify all the interconnections of a computer that is complicated enough for a self-driving car is going to take a semi. There will be so many wires. Okay, so that means this. Okay, John von Neumann, his vision is revolutionary. It's not just going like, yeah, we're going to reduce the transistors by another 50%. Nope, it is completely different. So now we can take a look at his actual contribution. Okay, so we'll go back to the other page. Okay, where is it? Okay, right here. And then we look up architecture. There we go. All right. So in terms of architecture, um, his contribution has to do with. Okay, I'm just reading a little bit here. I'm looking at the ENIAC. The architecture was based on the work of blah 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 inventors of ENIAC and its successor. Okay, so ENIAC is before that. Okay, so that makes sense. Anyway, so his contribution is it sounds simple. Okay, he's basically saying in order to instruct a computer what to do, instead of physically wiring and hardwire everything, let's just use the memory of the computer to also store instructions that will tell the machine what to do. That was the one change that he made. Okay, are we understanding the key concept here? Before, it's all based on wiring, and after, now it is based on the memory content of computers. Now, computers always have memory. Okay, so if you look at all the architecture before von Neumann architecture, they all have memory because they need memory in order to remember the data that they're processing. Okay, all the input data, all the output data, they all have to go into memory somewhere. So his contribution, John von Neumann's contribution, is basically to say, let's not just use memory to store the data that we're processing. We'll also use that to store the instructions, the very instructions, in order to tell the computer what to do. In other words, he essentially is a virtualization of how you specify what the computer is supposed to do because now it's all digital. It's all programmable, or more easily programmable. Because without his contribution, punch cards are useless. Okay, because punch card is just storing data. Okay, but if you need to change the behavior of the computer, you still have a massive amount of wiring. So that is connecting now back to this module. Okay, the module that we are talking about here. And SR latch, okay, the SR latch concept turns out to be the simplest memory device that we can make. It is made out of two NAND gates, which is equivalent to 8 transistors. So now the question is, but Tack, you only showed us the oscillation, it doesn't seem to be very useful. Okay, so what we'll do is we're going to work out the truth table. We are in 10 minutes. I don't think we have enough time to work out the entire truth table, so I'll give you the summary of the truth table. So the summary of the truth table is actually also here. Okay, so this truth table looks a little funky. Okay, the inputs are S and R. Okay, so that's pretty easy. Okay, we know how to read a truth table when we have two independent input Boolean values. So in this case, S and R are the input, Q and NQ are the output. The first row, I think we know how to read that. It simply means that if both inputs are 0, 0, okay, they're both zeros, then the outputs are guaranteed to be 1 and 1. Doesn't seem to be very useful, okay? The second row, yeah, pretty easy to read too. If the S pin is a 0, the R pin is a 1, then the Q pin is guaranteed to be a 1, and then the NQ pin is guaranteed to be a 0. Doesn't seem very difficult. Third row, everything just got flipped. Okay, kind of the same deal. No big deal. The last row is the funny one. Okay, and by the way, this NC is not node connectivity. It is representing no change. Okay, so what that means is if you change the input pins into 1, 1, it depends on what it was before. It preserves Q and NQ. Okay. So I'll let you guys continue to look at this, and then I'll go ahead. I think I'm going to do this trick again, but this time I'm going to use. Mm, yep, that'll work. And then I'll go back to Logisim. Okay, let me see. Where is my Logisim? All the way to the bottom. Oof, there we go. I forgot to turn the other one always visible. Always on top. There we go. Okay. So now what we'll do is we are going to play with this circuit. Okay. And what we'll do is pick one of the middle two rows. Okay, we'll pick either this row or this row over here so that Q and NQ would be no. So that before we do that, I have to re-enable simulation and reset the simulation like so. Okay, so this picture makes sense because it's corresponding to the first row of the truth table, right? Both inputs are zeros, both outputs become ones. Okay, no big deal. By the way, I cannot change both inputs to ones at the same time because it would take me one click here, and that is not going to be simultaneous with the change of the other pin. So the only way to do that is to really tie both of these together, but I'm not going to do that. Okay, so what I'll do is let's go for the third row. So on the third row, we change the S pin to a 1. We keep the R pin to be a 0. And the output is Q being a 0 and NQ being a 1. Okay, everything matches the truth table, right? We all good? So now what we'll do is we're going to change R from a 0 back to a 1. In other words, we are transitioning from the first row to the third row, and then from the third row to the fourth row in the truth table. So here we go. Change the R pin from a 0 to a 1. And you can see the outputs stay exactly the same. Then you guys go like, so maybe that's just the behavior of 1, 1 as inputs. Okay, so let's go ahead and erase this. Okay, and this time we'll go for the second row. Okay, the second row says the S pin is a 0, and then the R row is a 1. Okay, like so. Okay, so this is we just changed it. So we'll go from this state, which is the second row of the truth table, all the way to the last row of the truth table, which means the only thing I have to do is to change the S pin from a 0 to a 1. Okay, so we go do that. Okay, you go like, nothing happens to the output pin. So when both inputs are ones, and that's why in the truth table, it is represented by NC, or no change, because whatever it was before, it just maintained that state, with the exception of you cannot transition from 0, 0 as input to 1, 1, because in that case, it will start oscillation. Hmm? You want to see it oscillate? Sure. So the only way to make it oscillate is you have to basically get rid of one of the input pins and then have one single input pin to connect to the same. Uh, this is the only way to do it. Okay, so we change both to 0, 0. Okay, not a problem. Okay, Oh, it doesn't like it, right? What does it say here? It's a little hard for you guys to read it. Oscillation apparent. In other words, the Logisim, the software, through its own simulation, internally it's saying like, I cannot find a steady state because internal to Logisim is going through the spreadsheet approach that we were talking about, and it is noticing that, hey, how come I'm going back to a previous row? It looks exactly the same as a previous row, and that's how it can recognize that it is in an oscillation of some kind. So is that satisfying your curiosity? Okay, cool. So let me reverse the circuit back to where it was, reset the circuit. Okay, there we go. But the question now is, why is this circuit useful? Okay, because as a memory device, it is really strange, right? And by the way, the letter S stands for set, S-E-T, and then the letter R stands for reset. Okay, and it is also inverted. Okay, because when it's called active low, it means okay. So I'm going to put it into 1 1 again. Okay, so we'll put it into, let's say we will just put it into this state. So it is called active low because when the input is a 0, that's what we are doing to the Q pin. So that's why it's called active low. So in this case, we are basically saying, oh, because it is active low, this configuration is quote unquote setting the output pin Q, which means turning it into a 1. What do you think is the the abbreviation of NQ? Not exactly. N is just not. Yep, there we go. So we can preserve the state, okay, just like before. This is preserving the state. So if I change R from a 1 to a 0, once again, it is active low, which means if R is a 0, you are saying, I want to reset the Q pin. Reset is the same thing as, oh, we want to make it a 0. So that's exactly what's happening is when R becomes a 0, the Q pin becomes a 0. NQ is just a negation of that. So and then when you change R back from a 0 to a 1, it is preserving that state. And this is the simplest quote unquote memory device in a computer. Okay. It doesn't really feel like it is useful, right? Because by itself, it's like, how do we make use of this to make anything that is actually useful? So that's why we have the other mechanisms that are also kind of presented in the same module. So the next one is called a D flip-flop, and I basically give you a text representation of a D flip-flop. So if you go all the way to the end, then we end up with something that looks like this. Okay, so this is called a level level and clock sensitive and resettable D flip-flop. Okay, which is only useful to store one single bit. Okay, you go like, one single bit does not sound very useful to me. That is correct. So we can have a bunch of them. So when you hook up a whole bunch of those D flip flops together, it is called a register. And the concept of a register is central to the design of just about any processor out there. I don't care whether it's an ARM processor, whether it's a RISC processor, whether it's a Cisp processor, they are all based on registers. Okay, so that's kind of the roadmap of what we'll be talking about after exam one on next Tuesday. So we do have a lab tonight. Okay, so the lab tonight is NC and PD. Okay, so let me enable first. Okay, and at the end of this one, you have to turn in a Google Sheet. All you have to do is there'll be instructions of what you need to do. Okay, But you do need to know the access code. So let me give you the access code first. And let's see. The access code is under settings and show access code. Step master. Okay, so the access code is step master. I I think some of you can kind of envision why it's called a step master because we have been stepping through the NCPD thing. All right, I'll see you all in STEM 301. It's getting cold outside, so remember to bring take your jacket with you. Mhm.